If it's muted, it does. That's kind of cool. Power of power law. Let's just get into some examples. So the power of power law is what you do when you have an exponent on an exponent. Like this guy right here. We have a power, and then that power has another exponent. To figure out what happens, we're going to break this out into its pieces. So we're going to break it into factored form, then we're going to change it back into exponent form, and then we're going to calculate it to see what happens. So, factored form. An exponent just tells you how many times to multiply the base together. So if you look at a question like this, you have a base of 4 to the power of 2, and it's saying multiply that base 3 times. So this would turn into 4 to the power of 2 times 4 to the power of 2 times 4 to the power of 2. Right? Same idea, same fundamental principle as what we did right here. It's just now it's a little more complicated because you've got a weird looking base. When you do that, you've now turned this into a multiplication question where we learned that with multiplication, you can do what to the exponents? Add them. So this becomes 4 to the power of 2 plus 2 plus 2, which is really 4 to the power of 6. Factored form is when you take something and you break it up into all its multiplication, like what I did there and underlined in yellow. Exponent form is when you combine it all into one thing. Standard form is what happens when you actually calculate it. I don't know what 4 to the power is.
4,096.
Thank you. I was like, I need to steal your calculator. 4,096. Awesome. So we can do this like over and over and over again to kind of get a hang of it. Then I'm going to show you like a quicker way to tackle these questions. 4,096. This guy over here. Yeah, sorry, that's 4,096. I'll try to zoom in a little bit. Yeah, or get somewhere better. So B, we can do the same process. If you want to take B and turn it into factored form, the base is 3 to the power of 4, and you're multiplying it 2 times. So it'd be 3 to the power of 4 times 3 to the power of 4. That would be factored form. We learned last week when you're multiplying bases, you add the exponent. So this becomes 3 to the power of 4 plus 4. That means we have 3 to the power of 8.
It's 6,516.
6,516?
61.
Thank you. 6561 is the standard form.
Oh my god.
Now, like, that's fantastic. It's a little bit slow if you're going to break every question down like that, though. So there is a quicker way. It's good to understand why something's happening, but then it's also good to know how to most effectively get through a question, right? So when you're looking at this question, the next one, you have 2 to the power of 3, and then there's 5 of them. In factored form, that'd be 2 to the 3 times 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 2 to the 3. And it's kind of a pain to write out 3 plus 3 plus 3 plus 3 plus 3 to figure out what it is. So instead, what you can do is use our power of a power law. The power of a power law says that when an exponent has an exponent, you multiply the exponents together. So instead of doing 3 plus 3 plus 3 plus 3 plus 3, I could say this is 2 to the power of 3 times 5. I think that's quicker. Rather than doing multiple additions, we just do it one multiplication. That would give me 2 to the power of 15.
Wait, what did you just do?
So instead of adding and showing all these little additions, I could just understand that by doing 3 plus 3 plus 3 plus 3 plus 3 is the same thing as saying 3 times 5. because there's 5 of them.
Yeah.
So it's kind of like our quicker way through. Yeah. Question, are you good?
Oh, it's the Stanford's
Oh.
2,768.
3, 2.
768.
Thank you very much. All right, how I would show this. So I'll show you how I show like my work when I'm doing power of a power law. Typically what I do is I take a question like this next one, and I take the power 5, and I multiply it into the other exponents. And I show it like that. I circle it, and then I do a little arrow, and that shows multiplication. Then I could write this out as a to the power of 6 times 5. That's a to the power of 30. And you can't evaluate standard form with a letter, right? You don't know what a is, so you just leave it the way it is. That's the quick way to do it. So when you get good at this stuff, like that's what I would expect to see kind of all over your paper. There's like multiply, just times.
You just times the 2.
Yeah.
So like let's say there's the 5 3 times.
Yeah. Yeah. And it's just a quicker way of doing it than all those like adding. It gets a little bit more complicated when the base gets a little bit more complicated too. So if you look at E, I'm going to write E out in like long factor form so you can see what it actually looks like. And then I'll show you the trick to make it go a little faster. So if you have something like this, your base is 5a. The exponent is saying multiply 5a times itself 4 times. So I had 5a times 5a times 5a times 5a. Right? That's the factored form. We also learned last week that numbers can only multiply with numbers and letters can only go with the same letter. So if you looked at something like this, I could look at all the 5s and realize they all have exponents of 1. And I could rewrite this as 5 to the power of 4. Right? Because I have a 5 times another 5 times another 5 times another 5. And I could do the same thing with the a's. So I have an a to the power of 1, another a to the power of 1, another a to the power of 1, another a to the power of 1. That means I have a to the power of 4. And that would give me my exponent form. That's kind of the slow way to do it. But it would always work if you actually showed all your steps like that. A quicker way to get through it is to realize that this 4 would come into the brackets and go to all the exponents. So it's going to go to the exponent on the 5, and it's going to go to the exponent on the a, which is why it became 5 to the power of 4, a to the power of 4. Quicker way to do it. So for f, if I wanted to do f quicker, that means I would take this 3 and multiply it into the exponents. And it's only going to the exponents, not to the base. Right? It's not 4 times 3. It's going to be 4 to the power of 1 times 3. This would become 4 to the power of 3, a to the power of 2 times 3, which is 6. So 4 to the 3, a to the 6. Our power of a power law gets kind of tricky. It's like the first thing that really changes up. G is the same kind of deal, except now there's 3 things, right? There's a number, and then there's an A, and there's a B. I'm going to do it the quick way. The quick way is you take the exponent and you multiply it to the other exponents. I take this 3, I multiply it to the other exponents, including the invisible ones. So that would become 7 to the power of a, 7 to the power of 3, times a to the power of 3, times b to the power of 15, because I multiplied the 3 and the 5 together. Exponential, like if you were to break up into factored form, sorry. Like this is exponential form. I just did it quick. I think that would be there. Exponential form would be all that times 3 times 3 times 3. It would be a lot of them. If you want to try H on your own, I'll give you like a second to try it. If you can't do it, that's fine. If you want to just give it a shot to see how close you get, that's good too. And then maybe you see where you're going wrong. I'll give you about 10 seconds or so to try it. There's a trick to H that makes people make a big mistake on it. So if you're looking at H, a lot of people who get the power of a power law do a pretty good job of taking the 2 and multiplying it into the exponents. Then they write this out. There you go, negative 3 to the power of 2, a to the power of 12, and b to the power of 6.
That is like far off.
So you want to make sure you're multiplying the exponents. So 6 times 2 is 12, and 3 times 2 is 6 as your exponents. No, did you do 6 to the power of 2?
No, I didn't.
You did 3 times 2. Yeah, so you got to remember there's like an invisible 1 on the exponent. Yeah. With this answer, though, there is one thing that we made a mistake on. And it's why I want to show you this, because it happens all the time. And it's something that people make this mistake for like years, and it constantly gets them the wrong answer. We learned last day about negative bases. Right? If there's a negative number that you want an exponent, this 3 in here is a negative 3. So that means I need to put brackets around the negative 3 to make it negative 3 to the power of 2. The next thing we learned was that if you had a negative power or a negative base with an even exponent, that the number would always turn out to be positive. Right? Even exponents turn things positive. So my final answer, if I wanted to do it in exponential form, would become positive 3 squared, a to the power of 12, b to the power of 6. Because when you put negative 3 to an even exponent, it turns it positive. Teaching grade 10 exponent laws, that's probably the biggest thing people forget coming out of grade 9. Negative exponents to an even power gets rid of the negative symbol. If it had been an odd power, then I would have left the negative symbol. Cool, let's try a couple more. So if you look at I, now that we know that rule, we're going to take that 3, bring it in. We're going to put the negative 2 in brackets. So it becomes negative 2 to the power of 3. Then it's going to become a to the power of 5 times 3, which is 15. And then we're going to do b to the power of 1 times 3, which is 3. Now we can look at this power, like the negative 2 to the power of 3, and we can think about it and be like, okay, negative base with an odd exponent will stay as a negative. So instead of putting the brackets, I can leave the negative there and now get rid of the brackets because it's an odd exponent. So I have negative 2 to the power of 3, a to the power of 15, b to the power of 3. Yeah, so if you look at J, there's kind of 2 ways to do J. I would probably do it the way you just did it, right? But I also know that the power law would work a different way. So I like how that went, where you did this first. Oh, I can't write on my screen anymore. That first, and then to the power of 4. That's fine. I'll show you how they do it as a power, though.
Would it still be the right answer?
Yeah, I'd give that to you. So if you look at J, I'm going to do the same thing. I'm going to take the exponent, and I'm going to distribute it in. And realize it becomes an exponent on the other bases. So this would be 3 to the power of 4 times 5 to the power of 4. That would be the exponential form of that question.
For I, on your exponent form, for the like little, is it like -2
To the power of 3.
to the power of 3?
Yeah, was that a little rough to see? That better? Yeah. Was that the number that was messy? Yeah, okay. My rating is not fantastic, and it only got worse once I had to get started ready on this thing. So if you ever aren't sure about a number, just ask, and I'll definitely help you out. Especially like 5s and S's and stuff, it doesn't look good. So you can always ask. For K, we have an exponent on an exponent, right? Power of a power. So I take my exponent and I bring it into the other exponents. That gives me 2 to the power of 6 times 3 to the power of 4.
Could I do 5 to the power of 6 times 5?
So that's a good question. So then people like look at that and then they start doing other exponent laws, right? They start doing their adding of the exponents, or they start multiplying the bases, or they do something else along those lines. When you're doing your exponent laws and you're doing like your basic exponent laws, like the multiplication addition ones, these ones on the whiteboard, that only works if the bases are the same. If the bases aren't the same, like our case right here, then you actually can't change anything and you would leave it the way it is. So this would stay 2 to the power of 6 times 3 to the power of 4. And there's nothing else I could do to it because the bases are different. Kind of like having different letters, right? If I have an X and a Y, I can't combine those. A 2 and a 3, I can't combine them. They stay separate. Yeah, Damon. Yeah, man. So if you look at L, we take the exponent, we multiply it into the other exponents to get 3 to the power of 6 times 5 to the power of 3. You multiply the exponents together. Everything else stays the way it is. Awesome. That gives us our little rule that we can fill out here. So when a power is raised to another power, that's why I call it power of a power, simplify the expression by multiplying. By multiplying the exponents. That's called the power of a power law. At least that's what I call it.
What am I next?
How did you open it so easy? So
Right. It goes quick, yeah.
When I say something,
Yeah.
like,
Yeah.
Plus,
Yeah. Things do get difficult quick. Go ahead. Do you have a question?
Oh, no, never mind.
Okay. We will look back at our zero exponent law, which we kind of talked about last day, but not really. And how the zero exponent law can get a little bit trickier. So last day we learned that when you have division, you subtract the exponent. So if you look at this question, we have 2 to the power of 3 divided by 2 to the power of 3. Using our division law, we know that same base with division, we can subtract that to become 2 to the power of 3 minus 3. 2 to the power of 3 minus 3 is 2 to the power of 0. Which that's what we were doing last day. Right? We were like, what do you do when you have that? And you have to put the 0. If you don't put the 0 and you put nothing, remember that nothing means there's an invisible 1 there. So you have to put the 0 in. You don't just leave it blank. Now, if you think back, we know like from way back when you learned division in like grade 3 or 4, depending on when you got taught, you should have learned that anything divided by itself will always equal 1. So I'm going to fill that first blank in. Any value divided by itself is equal to 1. My like 8-year-old learned that last year, and so then he thought he was this great mathematician because then he's like, "What's 1,200,000 divided by 1,200,000?" And like he thinks he's so clever. It's just always one, right? So anything divided by itself gonna be one. That rule helps us with our zero exponent rule, because then if you think about it, 2 to the power of 3 divided by 2 to the power of 3 is just something divided by itself, which means it should equal 1. Which means anything to the power of 0 actually equals 1. That's why that's happening. Yeah. Tricky, right? So this gives us our zero exponent law. Our zero exponent law is that anything to the power of 0 is 1 automatically.
So the 2 at the top is 1.
Yeah, so like this guy right here would be 1. Like the answer is 1. Everything turns out to be that. If we're looking, we're just going to fill out some charts. Actually, I don't want to fill out the chart. Get rid of that. I don't think we need to fill out the chart. You don't need to fill out the chart.
Less work.
Below that, yeah, less work's always good, right? Below that says any value with a zero exponent is equal to 1. There's only one exception to that, and that's 0 to the power of 0, which you don't ever have to worry about. But if you ever had 0 to the power of 0, we call that undefined. Like that. The reason why is because your exponent law would be 0 divided by 0, and you can't divide something by 0. It doesn't work. You'll learn more about that next year. All you need to know for now, 0 to the power, or sorry, anything to the power of 0 is 1. That's your zero exponent law. So if you look, there's a whole whack of questions here. To the power of 0, it's going to be probably the easiest stuff you ever do, except for a couple of them. So if you look at this first one, we have 2 to the power of 0. Anything to the power of 0 equals? 1. Guess what the next answer is going to be?
1.
Yeah, right? 17 to the power of 0? 1. Not all of them.
Some
If you look at C, negative 8 to the power of 0 would be?
negative 0.
1.
Negative 0.
Now, if you look at negative 0, maybe. If you look at D, the answer is not going to be 1. D is going to be negative 1. Now, the difference between D and C has to do with your base. Go ahead.
What EOS people do?
Yeah. So if you look at the bases on C and D, remember brackets are really important to us. C had negative 8 as the base. D was really negative 1 times 7 to the power of 0. Like the negative wasn't part of the power. And that's why it became negative 1 times 1, which is just negative 1. We can do the same idea with E. So if you look at E, this is like negative 1. And then this turns into positive 1. It's like negative 1 times 1, which would give me negative 1 as my answer. So when you have something to the power of 0, it's always going to equal 1, but be careful on the negative symbol. Is the negative symbol on its own, or is it part of the power, and thus also turning to be 1? If you look at this next row, I'll let you try all of them. You can try to finish off the next 2 rows. I'll give you about a minute or 2. So if you look at F, the negative is part of the base, right? It's in the brackets. That means my overall answer is going to become positive 1. If you look at G, the negative is outside the brackets. That means the negative will stay there, and then the rest of it turns into 1. If you look at H, we have the exact same thing. Negative on the outside, 1 on the inside. If you look at I, we now have a letter to the power of 0. The rule is anything to the power of 0. So even if it's a letter, still going to turn into a 1. If you look at J, that's going to be 1 because the negative is inside the brackets. If you look at K, this thing would become 1 overall. If you wanted to do your power of a power law, you could do this. So you could make it a little bit harder. You could bring the 0 in. in which case you'd have 4 to the power of 0, a to the power of 0, and both of those things become 1, so it'd just be 1 times 1. Depends how you want to look at it. It's probably easier to just put 1, but that's another way to look at it. If you look at L, the negative is not part of the base, therefore it's negative 1. M is going to be negative 1. N is going to be positive 1. And O is going to become negative 1. So those should be all of your answers for the zero exponent law. Yeah, you did it. We're almost, gentlemen, we're almost done.
Why does it say Lakers 99? Because the Lakers destroyed Drake 99 to nothing in a football game. It was gone.
See, it's because Drayton's used to playing in the rain.
No, it's because
Drayton
Drayton's gone.
Drayton had a team of only grade 9s. And then they received this game.
Okay, we'll bring it back to some math here for a second. Just wait, please. You're not going to get overly tested on this zero exponent law. Like you might see like 1 or 2 questions on it. But what you will see a lot of is the power of a power law, the multiplication law, and the division law. Okay, so you are going to see those things, especially on your quiz on Thursday or on Wednesday. You're going to see a lot of questions focused around that. The zero law will exist. It'll be in there too. It's just there's not going to be a lot of them. Yeah.
Can you not explain it that's a decimal?
Yeah, so if you had something like this, I'll just write an extra question up here. So if you had 0.2 to the power of 0, like that would still be 1, 2. You're basically like that, or do you mean like this? Like 2 to the power of 0.5?
Yeah.
Like that? You can. That's called rational. We refer to them as rational exponents. And we will do stuff on rational exponents too. Mainly that's like a next year topic where it kind of kicks into high gear. But you could. And with numbers, you could put in your calculator to see what it equals. The very last question at the bottom there, if like it's a little bit overwhelming, right? Like
Really? It's just one.
right? It looks like a lot. It's not just going to be 1, but it looks like a lot when in reality it's just like a bunch of questions smushed into one big one. So the way that you tackle a big question like that is by following bed mass. We had talked about bed mass, right? Like how to do operations first. You should simplify inside your brackets first. That means do your multiplication rule, then do your division rule, and then do your power of a power rule. So if I was doing this question, and you will get questions that are like that in depth and look that intense, you start on the inside, work your way out. I'm going to try to color code it so you can kind of follow along. The first thing I would do is I would do this area here. I would do the numerator of the first set of brackets. Looking at what I circled in red, I have n to the power of 3 times n to the power of 8. I'm multiplying, so what do I do to the exponents? You plus them, you add them. So that means my top would now be n to the power of 11. Divided by, I'm going to highlight this area in blue. Now I'm going to do the bottom of that first fraction. That is an exponent with an exponent, right? Power of a power. We just learned what to do with that. What should I do when I have 2 exponents?
Times the exponents together.
Times them together. So that's going to become n to the power of 10. Now I have simplified my first set of brackets. Then I'm going to move on to the next set of brackets. I'll do them in square, kind of like this one, so it looks normal. The first thing I'm going to do is figure out what to do with the top of this division, or the first part of it. I have a power of a power. That's n to the power of 2 to the power of 3. Power of a power, you multiply your exponents. That becomes n to the power of 6. Divide by, and then n to the power of 2 is going to stay the way it is. Right? There's nothing happening to that one. And the 4 is still on the outside. So in black are things that stayed the same. I've color-coded everything else I've changed. So you can kind of see where it came from. We're still going to go. So this is going to be like a multiple step process. The next thing we're going to do is see if we can do any of our subtraction laws, right? Where we have division going on. Again, I'm going to color code it. So looking at the first set of brackets, if I have n to the power of 11 divided by n to the power of 10, what should I do to the exponents? Yeah, division means subtract them. Yeah, subtract them. So 11 minus 10 would become n to the power of 1. If you write the 1, that's fantastic. If you don't write the 1, that's also fantastic. Then I'm going to move on to the next set of brackets. I'm going to color code it in like purple here. So this is also division. Right? It's a fraction. It's just written out a little differently. When we have the same base, we subtract the exponents. So for us, this would be 6 minus 2. This would become n to the power of 4. Yep. What'd you get? Oh, close. Gotta go more. So if you're looking at this and we go to do the next step, we've done our multiplications on the inside. We've done our divisions on the inside. Now we can start to bring in our power of a power laws. So looking at this, I could take this 2 and bring it in. That would give me n to the power of 2. Right? We're multiplying the exponents. 1 times 2 is 2. The next thing we're going to do is we're going to take this. Oh, I don't want to use that color. I'll use this light blue. We have this guy right here. Power of a power. The 4 goes to that 4. And it's now going to be n to the power of 16. 4 times 4 equals 16. You've now narrowed it all the way down to your last step. You have n to the power of 2 times n to the power of 16. When you're multiplying like bases, what do you do to their exponents?
Add them.
You add them. That becomes n to the power of 18. Yeah, and that is the answer. So I don't know if anyone ever